All right, so last time we talked about fronts, which are boundaries between air masses, typically warm and cold air masses. And one of the things we pointed out is that these fronts are often inextricably tied up with low pressure systems in mid-latitudes, i.e. with mid-latitude cyclones. Mid-latitude cyclones. So today we're going to talk about these low pressure systems themselves. We're going to talk about how they form, how they evolve, how they get stronger, how they eventually decay. And this is kind of an important topic here for this latter part of the course for a couple of reasons. One is that these low pressure systems, these cyclones, bring us most of what we consider to be our sort of weather events, especially in the fall, winter, and spring months. A lot of what we would think of as weather, changes in temperature, winds, precipitation, things like that, are tied up with the evolution of these mid-latitude low-pressure systems. And the second reason this is important is because in a lot of ways it ties together a lot of the things that we've been doing here in this latter part of the course. Because as we'll see, these cyclone systems are fairly complicated, and so a lot of the pieces that we need to understand them are things that we've been building up bit by bit. So we'll get to all that, but first I want to step back and look at this from the big perspective. That is, I want to look at what role these systems play, these low pressure systems play in the global circulation. And one of the things you see, if you step back and you look at the Earth from afar, is you see that most of what we think of as weather, most of the disturbances in the atmosphere, are actually happening in a band of latitudes that's roughly 30 to 60 degrees in either hemisphere. That is, we're not talking about the tropics, we're not so much talking about the poles. It's really the latitudes in between, we refer to as mid-latitudes, from roughly 30 to 60, where most of the disturbances are happening. So, I've got an example of this down here at the bottom. This figure is showing water vapor. So the light shading here is water vapor and clouds as well. And so this is a satellite image, actually several satellite images pieced together to form a global perspective. And so I put over here on the right some shading, these bars, to indicate roughly the range of latitudes where most of the churning is happening in the atmosphere. So this is roughly the 30 to 60 degree band in either hemisphere. And just looking at the figure, you can kind of get a sense for this, especially in the southern hemisphere. It's clearest there. So if you look at the tropics, there's stuff going on, but it's not quite as much stuff. But then you look down here in this band, 30 to 60 degrees, and there's a lot of stuff going on. It's pretty complicated down here. There's a lot of churning going on. This is even clearer if we put it in motion and watch it evolve in time. So I'm going to step forward here, a series of images, a series of steps to look at how this thing evolves in time. And maybe just watch the southern hemisphere first, since that's clear. And you have this band down here where most of the stuff is going on. So let's go ahead and step it forward. So let's do that one more time here. So again, pay attention to what's going on down here in this band in the southern hemisphere. And you can see that most of the action, most of the churning was right down in that band, right? There's stuff going on in the tropics, but it's not as much. Most of what's going on, the churning in the atmosphere, is down here in this band. It's basically the same deal in the northern hemisphere. Northern hemisphere in this case is a little more complicated, either because of the season or perhaps because of the mountain ranges and the continents. There's much more land-sea contrast in the northern hemisphere. But let's step it forward again and pay attention to what's going on in the northern hemisphere this time. And you'll see again that it's mostly in this band of where the gray bar is, roughly 30 to 60 degrees, mid-latitudes, where most of the action is happening here. That's where most of the churning was happening, right in that band. Okay, so why is this? Why is it that most of the action, most of the disturbances are happening in this mid-latitude range? Well, the answer is pretty straightforward. And in fact, it's something that I've alluded to several times throughout the course. In fact, way back on the very first day in the course overview lecture, I even talked a little bit about this. And it basically just has to do with that mid-latitude band is where most of the temperature contrasts are happening. That's where your colder, denser air from the polar regions is coming in contact with the warmer air further south. And it's really that temperature contrast between the air masses that's driving most of this action, that's driving most of this churning. The basic idea is something that we've seen several times, which is that the colder air from the polar zones is, by virtue of being cold, it's heavy, it's dense. And so as a result, it wants to slide underneath the warmer air further south. Because it's heavier and denser, so it wants to slide underneath, and it wants to push that warmer, lighter air upwards. But this is happening on a very big scale, on a global scale. And because it's happening on a spinning planet, and we've got Coriolis force and the associated jet streams and all this stuff going on, this process of taking the colder, denser air and sliding it under the warmer air actually ends up happening in a pretty complicated way. And it's really the end result of that process that results in these low pressure systems, these mid-latitude cyclones. So the moral of the story then is that in the global perspective, mid-latitude cyclones, mid-latitude low pressure systems, are nature's way of sliding the colder, denser air from the polar zones, taking that cold, dense air, and sliding it southward under the warmer air further south. So that's the role that these cyclones play in the global circulation. They're on this complicated spinning planet with the Coriolis force. They are the way that you end up taking the colder, denser air and sliding it under the warmer air further south. You can actually sort of get a sense of that just by looking at the structure of these cyclones. So just got an example down here showing satellite image. This is visible satellites, basically just showing clouds. But we've got a couple low pressure systems. I'm going to focus on this one over here to the right. And we've got superimposed on the satellite image the positions of the cold front and the warm front here. You'll notice that both fronts are associated with clouds, as we talked about last time, because it's along the front where we have a lot of the lifting going on, lifting of the warm air. And in particular, along the cold front, we've got a fairly narrow band of clouds because the cold front is steeper, so it pushes the air up more vertically. Whereas along the warm front, we've got a wider, more diffuse band of clouds because the cold front is more shallow. It's kind of like a ramp. And so as the air goes up the ramp, you get shallower but more widespread clouds. Now, in the context of this global circulation bit, so remember that the colder part of the system is this part to the north and then behind the cold front, wrapping around here to the southwest, whereas this area over here to the southeast, that's the warm sector of the system. And with time, all of this wants to rotate counterclockwise around the low center. But generally speaking, the warm front tends to kind of get hung up and doesn't go very far, whereas the cold front goes a lot faster. And so it rotates around the low center more quickly and eventually catches up to the warm front. So what does this imply for the warm and cold air? Well, so what's going on as this cold air rotates counterclockwise around the as the cold front rotates counterclockwise around the cold air behind it is being pushed southward. And because it's cold and dense, it slides underneath the warm air down here in the warm sector. So the cold air from the north is being pushed southward underneath the warm air. And at the same time, this warmer air here in the warm sector is rotating counterclockwise as well, and ends up going up and over the cold air at the warm front. So it rides up the ramp at the warm front. So the end result of this process, of the evolution of this low pressure system, is to take the colder air, push it southward, underneath the warm air here in the warm sector, and the warm air here ends up being pushed northward and up and over the colder air. So we're pushing the colder air southward, and the warmer air gets pushed northward and up and over the colder air. So here's another example of a cyclone down here in the lower right. So we've got our low pressure system here, and it's the typical configuration that we've seen several times now, with the cold front extending more or less to the south and the warm front extending more or less off to the east here. So a couple notes about cyclones, a couple things to keep in mind when we're thinking about the characteristics of cyclones. So the first thing is something that I've mentioned a couple times, which is that cyclones account for much of what we consider or what we call weather events, including high winds, rain, snow, things like that. A lot of what we refer to as weather is stuff that's tied up with the evolution of these cyclones, and in particular with the fronts. So these boundaries between the warm and cold air masses is a lot of where this happens. You tend to get high winds in there. You often get high winds on the backside here of the cyclone as well. And then, as we've already seen, you get clouds and precipitation along the fronts and over the low center. So a lot of the things that we think of as weather, plus the temperature changes associated with the fronts as they pass by you. So a lot of the things that we think of as weather events are tied up in the evolution of these low pressure systems. Second thing to note is that cyclones develop, grow, and decay on a time scale of a few days to a week, roughly. So it takes one of these systems a few days to a week to develop, and then to grow, to become a strong system, and then eventually to die off. So that's the time scale that we're talking about for these weather systems. And if you remember back to our classification of motions that happen on time scales of a few days to a week or even a couple weeks are synoptic scale. So these mid-latitude low pressure systems, these cyclones, are examples of synoptic scale disturbances. Third point to keep in mind is that key features of these mid-latitude low-pressure systems are the fronts. So our cold and our warm fronts extending outward from the low center. Because that's where the actual boundaries are between the warm and cold air masses, and that's where a lot of the action is happening, especially in terms of clouds and rainfall. And then finally, the last thing that I want to note about these systems is that as these low pressure systems evolve, they're actually moving as well at the same time. They're propagating along the ground. And generally speaking, these low pressure systems, in most cases, the cyclones will propagate to the east or to the northeast as they evolve. So in most cases, a cyclone will propagate to the east or the northeast as it evolves. And the reason for that is because these cyclones are tied up pretty closely with the jet stream. In fact, we saw examples of this in our discussion of the fronts, because the fronts are regions of temperature contrast, and regions of temperature contrast are associated with the jet stream. So the jet stream tends to sit more or less right over these low pressure systems. And as a result, the low pressure systems tend to follow more or less where the jet stream is pushing them. so more or less following the jet stream. And for reasons that we'll see later, it's probably actually more common that they get pushed towards the northeast rather than directly east. It can actually be either way, but probably the more common case is that this low center, as it grows and develops, will actually be moving at the same time off to the northeast, say in this direction in this case. And so as it does so, it carries with it all of its features. So that the fronts and the low pressure center, all of these things are going to be carried along off to the northeast as the system evolves. Now, the evolution of these systems, the evolution of these low pressure systems is actually pretty complicated, as we'll see. In fact, you could make the argument that probably the biggest achievement of meteorology in the past century, in the 20th century, was developing an understanding of these systems. It took about 50 years or so, sort of the middle 50 years of the century, to develop an understanding of how these systems evolve. The first attempts to understand this were done by a group of meteorologists in Norway, sort of towards the end of World War I, so in the 1920s here. There was a relatively prominent meteorologist in Norway at the time named Bjerknes, who worked at a university in Bergen, and he managed to attract a bunch of other meteorologists to his university, and they dedicated themselves to this task to try and describe how these low-pressure systems evolve. And the end result of that effort is what's referred to as the Norwegian cyclone model. The Norwegian cyclone model, because it was developed by these guys working in Norway. Now, I should note that the book doesn't actually use that terminology. They instead refer to this as polar front theory. And, if you talk to a meteorologist, they'll certainly understand polar front theory. That's sort of the technical term. But most of us actually refer to this in day-to-day conversation, anyway, and water cooler talk, as the Norwegian cyclone model. So that's what I'm going to refer to it as, the Norwegian cyclone model. So the first attempt to describe how these low-pressure systems evolve. And it was pretty remarkable that they were able to do this as well as they did, because they were working on some pretty strict limitations. This was back in the 1920s, and at that point, they had no upper air data. They had no idea what was going on high in the atmosphere. They didn't even know about the jet stream. All they had was observations down at the ground. That's what they were going on. And even more than that, they were doing this in Europe, where these systems were coming in from the west, right? Because these systems moved towards the east, following the jet stream, more or less. And so they were coming in off of the Atlantic Ocean, and they had no data over the Atlantic Ocean either. So not only did they not have upper level data, they also had no data upstream over the ocean. But even with those limitations, just using the surface data over Europe, they were able to come up with a fairly accurate description of how these systems evolve. Now, it's limited. It's really just a description of how these things evolve at the ground. And there's not a whole lot of conceptual understanding of why. It's mostly a description. But nonetheless, it's a fairly accurate description of how these things evolve. So we're going to step through then what this model looks like, this Norwegian cyclone model. And then in the next screencast, we'll talk a little bit more about the mechanisms that drive it, pulling in stuff at upper levels. Okay, as with many things, people like to divide sort of the evolution of things into stages. You have to keep in mind that it's really a continuous process, but just to have a way to reference the evolution, we like to break the evolution down into different stages. So the first stage of the Norwegian cyclone model is a stationary front. So you'll recall that a stationary front is just a boundary between a warmer air mass and a colder air mass. So I should point out, I guess, that for all of these figures stepping through the cyclone model, I've got two perspectives. I've got sort of a simple little 3D perspective over here on the right with the cold air mass and the warm air mass. And then over here on the left is a representation of what it would look like on the surface map, with some arrows drawn in as well to represent the winds. Now at this stage, there's not a whole lot that's actually happening. Basically, this is just sort of the ground, sort of the breeding ground where one of these systems can develop, because you'll recall that the temperature contrast is what's going to drive the evolution of this thing. So the stationary front is just sort of the breeding ground for where these systems can get started. The second stage in the cyclone model is what's called the frontal wave stage, And the key feature of the frontal wave stage is that you start to get a little low pressure system that forms along your stationary front, along your region of temperature contrast. So, because it's shown out here, for instance, on the surface map, we start to get a little low pressure system center forming along the front. Now, the Norwegians didn't really understand why we get that started, where this low pressure system comes from. It turns out in most cases, as we'll see, that it's an upper level disturbance that comes in and actually starts this thing to form the low pressure center at the ground. But in terms of the cyclone model, this is just a descriptive model. So the second stage is we start to form a little low pressure system along the front. Once we form that little low pressure system, we also start to get some circulation counterclockwise around it, which means the colder air is going to start to move southward, which means it's going to organize, by definition, into a cold front because the colder air is advancing. And then the warmer air is going to start to move northward, which by definition means we're going to get a warm front. So here in this frontal wave stage, we start to organize into cold and warm fronts as well. So you can think of this as being the initiation stage then for the system. This is where we're just getting it started here. It's the initiation stage. The second, well, I consider, I guess, the third stage, the next stage of the cyclone model, is what's referred to as the open wave stage, And we can think of this as being our amplification stage. So if the previous case was the initiation stage, just starting our low pressure center, the open wave stage is our amplification stage, which means the system's going to grow stronger here during this stage. In terms of the low pressure center, what that means is that the low pressure gets deeper, i.e. the pressure drops. And as the pressure drops, you get a bigger temperature. As the pressure drops, you get a bigger pressure contrast between the low center and the surrounding air. So you start to get a bigger pressure gradient. And as you get a bigger pressure gradient, you start to get stronger winds. So the system's starting to amplify in this stage. And as a result, everything starts to circle a little faster around the low center. So you get a little faster motion of your cold front, and your warm front tends to organize a little bit better here. And so this is sort of the classic structure that we've looked at several times, where you've got your cold front starting to move to the south or southwest, and your warm front usually is extending off more to the east than they're showing here, but it might extend off to the southeast as well, as they've drawn it. Over here's the 3D perspective. The cold air starting to push its way southward underneath the warmer air, whereas the warmer air is starting to get pushed northward up and over the warm front. So that's the open wave stage, or amplification stage. The next stage under the cyclone model is what's referred to as the mature stage. The mature stage. This is the strongest stage of the system. This is where it's reached its peak intensity. So you can think of this as the peak intensity stage. And what typically marks the mature stage, by sort of the definition of the beginning of the mature stage, is when the cold front wraps itself around and first starts to catch the warm front. That's what we think of as the initiation of the mature stage, when the cold front first catches the warm front. You'll recall that as the cold front wraps around and catches the warm front, it forms an occluded front, where you've got cold air on either side of the boundary. So here's the 3D perspective over here, where you've got the colder airs wrapped around and actually caught the warm front over here, and the warmer air that was there gets forced upwards. So the mature stage, this is what we think of as the peak intensity stage. Following the mature stage, if that was peak intensity, you would guess the next stage might be the decay stage. And so that's the occlusion stage. So at the occlusion stage, we get this occluded front here where the cold front has caught the warm front, extending over a greater length of the frontal boundary here. So here, as you can see, the occluded zone has extended quite a bit southward along the frontal boundary. And it kind of zips up along the frontal boundary as the cold front catches the more and more of the warm front. You kind of zip it up along the boundary, forming the occluded front. Now, what happens here in the occluded stage is that you've managed to take the cold air and you've wrapped it all the way around the system. So our cold front is caught up to the warm front, and so our low pressure center is now surrounded by cold air. In a sense, we've taken the boundary between the warm and the cold air and pushed it further south. It's way down here now. And so as a result of that, you've cut off your low center from the temperature contrast that was driving it. And so at this point, it's starting to decay. It's starting to die off. So we can think of then our occluded stage, our occlusion stage, as the decay stage of the system. Here's what it might look like if you put it on a weather map here. So our different stages of the cyclone model. So we start with our stationary front here, our boundary between our warm and our cold air. The next stage is the frontal wave. That's our initiation stage, where we start to form a little low center at some point along the front, and you start to get some circulation and organizing into cold and warm fronts. Past the frontal wave stage, we hit the open wave stage. And at this point, we're in the amplification stage. So the system's getting stronger, the pressure is dropping in the low center, giving you bigger pressure gradients and stronger winds. And the cold front starts to move faster around the low center. That leads us into the mature stage, when the cold front first catches up to the warm front here. So over here, as you can see, the cold front and the warm front were separate, but when they first start to come together, that's what we think of as the mature stage. And that's typically the strongest stage. That's when we've got our lowest pressure. It might actually continue to decrease pressure a little bit beyond this, but right around this time is when we hit our lowest pressure in the system, strongest winds, all that kind of stuff. And then with time, more of the cold front catches up to the warm front. You form this occluded front along a greater length, and you wrap the cold air all the way around the system. And so at this point, you cut off the low center from the temperature contrast, and it starts to die off. That's our decay stage. That's our occlusion stage. And then finally, sort of the end result of all of this, going one step further beyond this part of the model, you sort of cut off your low center completely from the temperature contrast. So you've wrapped cold air all the way around. It becomes sort of an isolated little low center. Temperature's contrast is way down here, and so the thing's just going to decay. It's just going to die off at that point. So again, stepping through it, stationary front, that's sort of the breeding ground. Leads you to frontal wave, that's the initiation. Leads you to open wave, that's amplification. Leading to mature, that's peak intensity. And then occluded or occlusion stage, it's decaying at that point. And then finally, cutoff low center. It's not in contact with the temperature contrast anymore. A couple things to note about this. You'll note that as they've sketched this in, this low center is going to be propagating off towards the northeast. Right? It starts off here, sort of over, I think that's Tennessee, and then it ends up here above whatever, up in Canada, I guess, above the Great Lakes. So this whole thing is sort of propagated off towards the northeast with time, as we mentioned before. So the whole system, as it evolves, it propagates off towards the northeast. Second thing is just this idea that the role that this is playing in the global circulation is to drive the cold air southward under the warm air. You can see how that's happened because we started off over here with this frontal zone, the stationary front, passing more or less through Tennessee. But as time evolved, and as the cold front wrapped around the system, we took the cold air and pushed it southward, eventually wrapped it all the way around the low, and the resulting frontal boundary has been pushed southward. So we've pushed it way down here over northern Florida. So we've managed to take the cold air then and push it further southward underneath the warmer air. Okay, that's the Norwegian cyclone model. That's more or less how these weather systems work. Now, as I mentioned before, the Norwegian cyclone model is really just a descriptive model. And in more than that, it's really just a description of what's going on at the ground. So in order to get a deeper understanding of this, in order to explain why the cyclone forms and amplifies in the first place, we're actually going to have to start tying this in with what's going on at upper levels. And this is where we're going to bring in a lot of the building blocks that we've been building little by little through this second half of the course. And we'll do that in the next screencast.